Yeah, it's Math C time. So we got this conjugate root theorem here. Okay, what it says is if you've got a polynomial and all the coefficients of this polynomial are real numbers, you know, like if you had pz equals 8z cubed minus 2z squared plus 3z minus 5, right? That's got real coefficients, the 8, the minus 2, the 3. Okay, you don't have any i's in there. Like you could have a 3iz. That one, no. This theorem won't work for that. All right. So, if it has these real coefficients, and if you know that a particular number is a root, a particular complex number, you know, that actually has an I as well. I mean, 5 is actually technically a complex number, but it doesn't have an imaginary part. So if you had 5 plus 4i as a root, what this thing says is that the conjugate is a root. So that means that implies that 5 minus 4i also a root. Okay, this is what this theorem says. Alrighty. And one interesting thing that comes out of this is, since these complex roots always come in pairs, then if you've got an odd degree polynomial, right, so if you've got a third degree polynomial, since the complex roots can only come in pairs, the third root cannot be complex. Okay, it's got to be real. So you got to have at least one real. And just to see what this looks like, okay, here's an even degree polynomial. If you graph it, it could be a parabola. Okay, if it's degree 2, it could be this shape. If it's degree 4, etc. Okay, and if you're graphing this, your axis could be down here. Okay, in which case it's never going to cross. That's why you're not going to get a real root. Okay, and if this parabola was down here, you would get 2 real roots. Okay, you get these imaginary roots if you graph it. It doesn't cross your x-axis. Okay, and of course, if you've got odd, like this, etc., because there's no way doesn't matter where you draw an x-axis along here, this thing is always going to cross, because it goes from positive infinity to negative infinity. Hope that made sense. Alright, the problem that we're going to do next, here's my example. If 5 plus 5 square root 2i is a root of this particular third degree polynomial, find the other 2 roots. Okay, so we know 5 plus 5 square root 2i is a root, then z minus that is a factor, right? Anyway, we automatically know that 5 minus 5, right, the conjugate, is a root. Yes, yay, okay? This is what the conjugate root theorem tells us. So we got 2 of the roots already, so we only need 1 more root. But anyway, we can write this as if we write this in factors, it's going to be that times whatever the last factor is, you know, some number a, right? Find this root. Okay, that's what we have to do. And just out of interest, in the last example, I had something like this. Okay, let me just cross this out for a second. I had like pz minus q, or something like that. Plus q, you know, I might have. Okay, to find p and q. In this case, I know p is 1. Okay, because I've got just a 1 there, and it's probably getting confusing. Forget it. All right. Anyway, when we times these first 2 together, we've been, you know, this is sort of this factorization thing we've been doing earlier, so we're going to sort of combine this together now. And you could multiply all these out, but just remember that this thing is sort of going backwards from the dots rule. That's what that whole thing is, okay? If we were doing backwards in the last examples, we would have taken this and used the dots rule to put the minus and the plus. Okay? So that's what we've Okay, so now let's expand this whole thing. Okay, this z minus 5 squared, that's z squared minus 10z plus 25. I get this 5 square root 2i squared. We know that this is altogether it's going to be a plus because we've got a minus and we've got an I squared. It makes it a plus. We've got 5 squared is 25 and square root of 2 squared, which is 2. So we've got 25 times 2, which is 50. A times z minus a. Alright, which equals z squared minus 10z plus 75 times z minus a, I want to factor. And all this has to equal that. Okay, has to equal z cubed minus 8z squared plus 55z plus 150. Okay. So just again, let's multiply this out. Z cubed. Let's see, minus a z squared minus 10z squared minus 10 a z plus 75 z minus 75a. Oh, got confused there a sec. Alright, so we've got a z cubed that matches. Now I've got this weird, okay, so I've got this minus 10 plus a z squared. Then we got, let's see, let's put it this one, plus 75, 25, that's 75, minus 10a z, minus 75a, okay, this equals this. I've already got a minus, so 10a equals 8, a equals 0.8, okay, 0.8? What am I doing? 10 plus a equals 8. Okay, and a equals minus 2. Okay, so the roots are 5 plus 5 square root 2i, 5 minus 5 square root 2i, and minus 2. Okay, let me just quickly, to finish off, just show you why this conjugate root theorem works. If z is a root, then if you plug z into your polynomial, you get 0. Okay, so we want to show that then this is also true. If you put the conjugate in to that polynomial, you get 0. Okay, so the first thing is to realize that this is true. Okay, the conjugate of the polynomial, when you put this particular root in, is 0. Okay, just because 0, the left side is 0. Okay, the right side is 0, so the left side is 0. The conjugate of 0 is 0. Now, you write out your polynomial. Here's a way to write it out is this. N minus 1 times z. So this is just a general form for writing out a polynomial. Okay, and z plus, and so on down to a1 of z plus a0. Okay, so this is your different powers of z. Alright, so now z, the conjugate, you could put a conjugate line over all of this, or realize that this is the same as this. Put a conjugate line over these separately. Etc. Okay, this is because this rule, if I have two things added together and I do the conjugate of them, it's the same as doing the conjugate of them separately. Okay, so if I have z is a plus bi, w is c plus di, so z plus w equals a plus c plus b b plus di. Alright, z plus w conjugate equals a plus c minus b plus di, which is the same as a minus bi plus c minus di, which is the same as this is z conjugate and this is w conjugate. Okay, so using that rule we can write this like this, which we can then, the next step is to write this like this. Now the conjugate we can reduce to just on the z's, because an is just a constant. If you times a constant by a conjugate, yeah, so look, if you times a constant times a complex number and then conjugate it, okay, like here I take a constant, I times it by a complex number, so I get ka plus kbi, and now if I conjugate that, I'm just going to get ka minus kbi, which is the same as if I had just taken the constant and times it by the conjugate. Okay, I would have got the same thing. Okay, so probably not the best explanation, but that's the best you're going to get. Alright, so an, and now we can show that this equals an times just z to the power of n. Okay, so I've reduced this conjugate line each time. I'm just reducing it one more time. Okay, and this is, so this, you have to show that this, a number to a power, a complex number to a power, and then conjugated, is the same as if you made the conjugate first and then raised it to the power. And just, let me just show just graphically what this means. Okay, and this is my z. My conjugate is going to be just, it just flips the I. Okay, it's a mirror image, so I've got this particular angle. Now if I have this z to my power n, I've multiplied my angle by n, basically, and I've lengthened or shortened depending on the magnitude of z. But it's going to be exactly the same in the opposite direction. Okay, this z conjugate to the n is also, it's going to have the same angle, but just the opposite way. Okay, so this, it's going to still be a mirror image. Okay, it's still going to be a mirror image, which means it's still the conjugate. That means that this is still the conjugate of that. Alright? And which means now this is showing that this is equal to the, just shoving the conjugate into that formula, which therefore means p of z equals 0, which means z conjugate is a root, and we're done.